Welcome to class, and thanks for being here. We're continuing on in Chapter 3, and Chapter 3 is basically all about functions. And today we've come to a point where we're going to talk about what's called function composition. So this is section 3.4. Just as a quick reminder, in 3.1 we introduced functions and how you could represent them in lots of different ways, in graphs, in equations, as ordered pairs, lots of interesting ways to represent them in tables. Then in 3.2, we focused real heavily on finding the domain, particularly in the case when the function is given in terms of an expression like f of x. And remember there we were worried about division by 0, or taking the square root of a negative number, or an even root of a negative number. And then in 3.3 we talked about sort of rates of change, right? So that was that main equation that we had there was rate of change, and what rate of change was measuring was sort of how quickly the function was going up or down, right? So a negative rate of change meant it was going down, decreasing, positive meant it was going up, and the bigger or smaller those numbers are in magnitude, the bigger that change is, right? So that's what we were doing in those sections. And now we're coming to the place of what's called function composition. And let me go ahead and show you what our objectives are for today. So here we have our objectives for section 3.4. And this week it's a little bit nicer than last week. We don't have 3 sections to cover, just 2 sections. There are some weeks where we'll need to cover 3 just because of the schedule for the semester. But this week we'll just cover 2. And here, the first thing that we want to do is talk about combining functions using algebraic operations. And there's only a couple of questions in Affinity, but this is really important, especially if you want to understand what function composition really is. So we're going to talk about something else, right? Something that's not an algebraic operation. And here by algebraic operations, they mean things like addition, multiplication, division, exponentiation, that sort of regular stuff that you're used to in algebra. But when you're dealing with 2 functions, there's a new way to create a new function from 2 given ones, and it's called the composition, right? So we'll talk about what that composition is. And again, the best way to understand it is to try to understand what these algebraic operations are, right? So we'll be able to add functions, divide functions, just like we did for numbers, but now for whole functions, and that'll be our sort of doorway into understanding compositions. And then we'll focus on evaluating compositions. For the most part, section 3.4 is about like the affinity homework, the things that we're asking you to do there are about evaluating compositions of functions. And they may give you functions in terms of a table, they may give you functions in terms of a graph or an equation, and they want you to go through and evaluate various types of compositions, okay? So we'll talk about how to do that evaluation. One of the trickiest things with compositions is writing out what the domain is. And the reason is that the composition depends both on the domain and the range of both functions. So we really have to be very careful about identifying the domain of a composition of 2 functions. So we'll talk about that. And then something that I don't think we even really have an example with in our notes for today, but there is, I think, 2 questions at the very end, is to decompose a composition into its component functions. And we'll sort of talk more about what that is, but I'll leave that to ask questions on our sort of Monday sessions. If you guys are having trouble with that one, I think you'll be able to understand it if you get the previous 4 objectives there. But I should say that that last objective is particularly important for those of you going on to calculus, right? To recognize when some expression is a composition of other functions is really important because it'll indicate the steps that you'll take in calculus, right? So there's going to be some important rules that depend on sort of compositions of functions. Okay, great, so Allie's pointing out that there's a video in the book about decomposing functions. And that's a good point in general. I've had some students email me and they were worried about certain sections or wanted a couple more examples. And just as a reminder, if you open up the textbook and you have the online version, you scroll to the end of those sections, there are videos at the very end that give you some good videos there in terms of good examples and stuff like that. And then also in the affinity homework itself, there are videos that you can watch that can help you out. So we won't really get into too much detail there, but I think you can piece it all together from the other objectives. Okay. Okay, so here's the definition of the algebraic operations, but let me draw a picture first. So I'm going to sort of draw my board here and remind you of sort of the picture that we had for a function. So what I was telling you to sort of think about a function as was sort of this black box, and you label the box something like, you know, the function letter. So we said something like f, and it has certain inputs, right, which we were typically labeling x, and then it goes through some process, and again, we get some output, and if we throw in the input x, we labeled the output f of x. And again, this was the domain, and this was the range. Okay, so that again was the sort of the picture that you should have of what's going on with a function. And what we're going to do now is we're going to take, say, two different functions. So maybe we have two separate functions, f and g, so two separate boxes here that take inputs and produce outputs. And we're going to combine them together to produce a new function, right? So you could do this with all the familiar algebraic operations, so like addition, multiplication, division, and subtraction, even exponentiation, basically any other of the operations that you would have for the numbers you can extend this way. But we'll focus just on addition, subtraction, multiplication, and division, right? So you can take two functions, which you should be visualizing like this, right? Not like a number, but as a whole machine that takes inputs and outputs, and you can piece them together into a new function. Okay, so let's see how we can do something like that, and we'll take sort of a top-down view of the picture here. So we also sort of saw this picture in the textbook. Let's say we have a function here, f, and we can sort of think about it like this. So here we have this input x, we have the function f, and then its output f of x. So this is just looking at that picture that I had before, sort of from above. And we can take a second function, let's call this one g. It also has an output, it also has an input x, but now its output is going to be labeled g of x. And I think I hear some noise that's showing up here, so let me see if I can mute off the mic here. What do we have? Okay, that should kill it. All right, so this x is going into this g and producing g of x, right? So we have two different functions here, and what we want to do is just combine them into a single function, okay? So I'm going to put a larger function here in sort of green, and what this function does is it has just one input. Okay, so let me erase these yellow pieces here. It just has one big input here, which I'm going to call my x. And then what it does is it splits that x up into two pieces, right? It duplicates x. And it sends one x over to f, and it computes f of x. Okay, so then it goes through this, and it computes f of x. And then it does the same thing with g, right? So it duplicates the x, and then it puts it into this machine here, and then it outputs g of x. Okay? And I'm going to call this big machine f plus g, right? So this new machine is the sum of the two functions f and g, and its output, the way we get it is we do the following. We take f and g, and we add them together, okay? And that's our output of this function, and so we get what's called f of x plus g of x, okay? And so this is the picture, right? We take our x in, it's duplicated, it's then plugged into the two functions that you're given, f and g. We produce those outputs. Then whatever we get from the output, we add together, and that's the new output of this new machine, f of x. I'm sorry, f plus g. So just coming back to this, what I talked about right here, I just drew in a picture this formula. So this is defining the function f plus g. That's what you see here. And we're saying what happens when we throw in the input x? Well, it's going to be equal to throwing the input into f, throwing the input into g, and then adding those two things together. Okay, visually it looks something like this, right? So throw it into f and g, get the outputs, and then add them together. And this is sort of the process that you'll have in mind when you actually evaluate a function and try to compute something like f plus g at a given input. Okay, and you can do the same thing here for all of these, right? So instead of instead of adding, you could have subtracted, right? So we could produce a new machine here that's f minus g, and the only difference would be that, okay, we duplicate x again, but here we subtract. So we subtract the outputs and we get f of x minus g of x, and that's exactly what this formula is saying on the second line. If I want to evaluate the function f minus g, so this is the subtraction of the two functions. If I want to evaluate that new function at x, well, I evaluate x at f, I evaluate x at g, and then I subtract the two of them. Right? And that's what this output is saying. For multiplication, I just multiply the two outputs, and then for division, I just divide the two outputs, f of x over g of x. The only thing that you have to be worried about in the case of multiplication and division is that you don't divide by 0. So you have to be sure that whatever you get from this g of x output here is not 0 when you're trying to produce the function that does the division, okay? And the picture here, I think, is even more complicated than the formula, right? This formula is more than enough to evaluate everything, but it's the picture that you should have in mind if you want to try and understand what function composition is going to do. Because what we'll do with function composition is we'll sort of put these not in parallel with one another, but in series. So you send x through f, and then you get the output, and you put that into g, right? So that's going to be sort of what we do for a function composition, and I'll draw that picture for the composition we get there. And the composition is a whole new operation, right? It's not something that you could do with numbers. You can't take like the composition of 2 and 3. It just doesn't make sense. So it's a whole new operation like addition, multiplication, or subtraction, but just for functions. Okay, so these are the formulas. Let's actually go through and do some examples so you can see how to use the formulas, right? So maybe that was a bit abstract, and in Infinity they're not going to ask you to draw anything like that, but they will ask you something like this. They'll say, let f of x be the function 5x plus 7. And now we should be getting a sense of like sort of what the graphs look like for these as well. So this should be a line with slope 5 and y-intercept of 7. So graphically, that guy's a line. And then we'll also look at g of x is equal to negative 2x squared. And the x squared, that's one of those parabola shapes, right? So here we've got two functions, f of x and g of x, and we want to combine them together to form some new functions. So we're going to do the following. We'll work one by one through the following list. So we're going to look at f plus g. Okay, so we want to add these two functions together and then evaluate that at the input of 1. Okay, so the question here is, what happens when I plug 1 into the sum of these two functions? Okay. And then the next one we'll do is subtraction. So we'll do f minus g, and we'll also evaluate that at 1. So we can see sort of the connection there. Then we'll pick a different input. Instead of 1, we'll do 2, but we'll do multiplication, f times g, evaluated at 2, and f divided by g, evaluated at 2. And again, be very careful here. Lots of students confuse this the first time they see this as f plus g times 1. This is not f plus g times 1. This is the sum of the two functions, then evaluated at 1. Okay, not the same thing as multiplication here. So be very careful with this function notation. Okay, so let's just go back to the formula, right? So this is the sort of thing that they'll give you in Infinity. They'll say evaluate this sort of thing. And what you want to do is just go through this and simplify it using the definition as much as you can, right? And the definition of f and g that we have up here, so you get down to a number, okay? It won't always be a number. Sometimes they'll ask you for something like f plus g evaluated at x, but here in these cases, since we're plugging in numbers, the output will be a number. It could be the case that it's undefined, but we'll have to sort of think about that maybe in this case here. So we want to make sure that g of 2 is not necessarily 0. So just coming back to that definition, what we have is f plus g evaluated at some x is f of x plus g of x, okay? So let's use that for that first one. So there, you're just going to plug in 1 into f and 1 into g. And at this point, when you're showing your supporting work, you can even write this step down, right? It's important that, like on an exam, you write something like this down so you show us that you know what addition is. And if you make a mistake later on, we can at least give you some partial credit for knowing what function addition is, okay? Because it's tempting to just plug in 1 into both functions and add them together in your head, but it's best to show as much work as possible. Okay, I'm going to just sort of like put these off to the side because the next equal sign that I write is not going to be equal to this guy, but equal to the previous step up here. So now what we do is we evaluate this function, f, at 1. Okay, so in the chat box, go ahead and evaluate f at 1. And let me know. And I think I see Charles here has a question. I'm sorry, Wilson. Where does 1 come from again? I just made up the 1. So here in these infinity problems, they're going to be asking you about different inputs. And here we're just saying we're plugging in 1, we're plugging in 1, here we're plugging in 2. So it's just part of the statement of the problem. Just like up here, you know, like there's no reason to take this as f, it's just part of the statement of the problem. Okay, and everybody sees that it's 12. And I'll just add an extra step here so you guys can see. I'm going to put in parentheses here. Everywhere I see an x, I'm going to replace it with 1. So that's 5 times 1 plus 7. So that's where everybody's getting 12 from. 5 times 1 is 5 plus 7 is 12. Okay. And then for the second one, that's g of 1. Everywhere I see a 1 in this expression, I'm going to replace it. Everywhere I see an x, I'm going to replace it with 1. So what do we get for g of 1? Is it positive or is it negative? Something that students kind of mix up often. Okay, so negative. Yeah, in this case, it's negative 2 because it's actually negative 2 times 1 squared, right? So you don't take that negative inside of the square. Some students will mess that up. Okay, so what's the overall value of f plus g evaluated at 1? This was 12. And this guy is minus 2. What do we get? 10. Perfect. So we have a new function, right? We threw in 1 into this new function. It was the sum of f and g. We first threw in 1 to f, threw it into g, figured out what those two values were, and then added them together to get to 10. Okay. So with that said, try to do the subtraction, right? Let's see what the difference is between these two. There's not much difference with subtraction here because when you're doing subtraction, you need to compute f of 1 and g of 1. We've already done that, right? So what do we get when we subtract? And by the way, don't be confused with this negative here, right? So this isn't a minus. This isn't like a subtract. This is plus a negative, and plus a negative you write as a subtraction. Okay, so almost everybody's getting 14 here, I think. Yeah, everybody's getting 14. So let's just see the difference. I'm just going to modify what you see up here because it's not going to change things very much, right? We're just changing that last step, okay, in that picture that we were saying before. So here I'll do f minus g evaluated at 1. The difference is now here we would get f of 1 minus g of 1. So here we would get a subtraction, right? So we're still plugging in 1 into this function and 1 into this function, but now we're using the operation of subtraction. So these are the two outputs. We're subtracting. Negative, negative now makes this one a positive. So now we get to 14 for this one. Okay, so that would be that guy. F minus g at 1. Okay, and you could do, you know, f over g at 1 and f times g at 1, and it'd be a similar sort of thing. You would just replace this operation, okay? But now let's change it so that we're plugging in at 2. And again, Wilson, you know, here I'm just making up the 2. It could have been whatever number. It's just part of the problem here. In infinity, they'll give you lots and lots of different input values. Remember, this is the input, so this is in the domain. This is the output, so this is in the range. Okay, so I'm going to erase these two guys, and now let's focus on f times g evaluated at 2. And notice how the parentheses work here, right? This is the actual function f times g. That's that whole machine. And then we're saying plug in the 2, okay? So let's go back and use the definition now. What does it really mean? Well, it means you plug in the 2 into f, and you plug in the 2 into g, and you multiply them together, right? So that's this formula here. Okay, so just coming back. Okay, so here we are, right? So here again, we'll just plug in the 2 into this function. We get 5 times 2 plus 7. And then over here, we're going to plug in the 2 into this function. That's negative 2 times 2 squared. Okay, so this is now just sort of a calculator problem. Multiply it out and then let me know. And hopefully that's enough time for everybody to write it down and that sort of thing. So if you have that value. Let me know. Okay, Angelique's got negative 136. Diana's got negative 136. I see a positive in there. In this case, it's going to be negative, right? So this square here is going to make this 4, and this whole thing here is negative 8. Right? It's a negative times a positive. And then this guy is 17. So yeah, 136 here. Negative 136 is the output of this one. Okay, and if we were to plug it in at a different value, we'd get a different output, right? So this is what's going on with that. Let's now do f divided by g at 2, okay? What do we get for f divided by g at 2? So let me know in the chat, and then we'll do it here on the board. Looks like everybody's getting through this pretty quickly. Okay, perfect. Yeah. So f of 2 was the 17, and g of 2 was the negative 8. Okay, so once you know the outputs, you can get all 4 of those expressions really quickly, right? So I would suggest if it's asking you to do a whole bunch of things with the same input, that on the side you compute something like f of 2 and g of 2 and then just use that so you don't have to keep rewriting over and over. And that's sort of what I did here, right? I just said, oh yeah, f of 2 was 17, g of 2 was negative 8. And if you have that work on the side or somewhere else, then that's clear, okay? Yeah, and the decimals should be fine too. In Desmos, in Affinity, any sort of decimals that you put in, as long as they're equivalent to the fraction, should be counted as correct as well. The nice thing about the decimals, it tells you sort of, how close to a whole number you are, right? Like, so the negative 2.125 tells you that you're really close to negative 2, whereas negative 17 over 8, maybe it's not as clear to you that that's the case. Okay, and then realize that there's a graph here as well, right? So I could take the graphs for these two functions and then sort of put them together and get a graph for this whole thing. I guess I should say there's another way to do this problem as well. You could have computed a formula for f times g, right? Like in terms of x, and then plug in the 2 afterward. But here we're sort of just computing things right away. Okay. Sorry, Wilson, I didn't see your negative 136, but Victoria's saying it here, 17 times negative 8. So this was the 17. There was the negative 8. Okay, so a quick question here. Let's change it up. So we're done with question number 1, but I want to ask something about this because I think there's a couple questions in Affinity along these lines. What is the domain of f plus g? Right. So, what is the actual domain here of f plus g? If you guys have it, just put it in the chat real quick, right? And then we'll discuss. But hopefully this gives everybody enough time to maybe think about it, and then first person to put it in. Domain. So what can we plug in for inputs into this function f plus g. And here I'm specifically asking about these guys up here. Right? So these particular f and g. Oh, maybe this is tougher than I was expecting. What about these? What about this one? What's the domain of f? Let's start with maybe simpler questions. What's the domain of f and the domain of g? Remember, the domain is the set of all things you can plug in. So there's going to be infinitely many. Yeah, so Brian has it here, negative infinity to infinity, right? I mean, we're not dividing by 0, and we're not taking the square root of any negative numbers there. So that domain is negative infinity to infinity, and this one is 2, okay? Same reason. We're not dividing by anything. So those two domains are negative infinity to infinity, and that means the domain of this function is also negative infinity to infinity. Because here, in order to compute f plus g evaluated at x, x has to be in the domain of f and the domain of g, right? And these overlap everywhere. So that's what's going on with that. Another way to solve this would just be to get a formula for f plus g at x. So you could get that like this. So f plus g evaluated at x would be 5x plus 7, that's f, plus negative 2x squared. And then if I just rewrite this as a quadratic, it would be negative x squared plus 5x plus 7. So typically we write it with descending powers. And you can see this is a quadratic, so the domain should be negative infinity to infinity, right? Just by domain considerations. But one way to think about it here is it's the stuff where you have to be able to plug into f and you have to be able to plug it into g. So both. Okay. Cool. So that was negative infinity to infinity. Let's just do another quick example. I'll go through this one a little bit faster than I did the previous one because it's the same sort of thing. And just a little more complicated function. Okay. So ones where you have to maybe think more carefully about the domain. So this is question 2. The first one's going to be the function 1 over x, and the second one is going to be the square root of x plus 1. So the domain of this is all real numbers except for 0. And the domain of this guy is everything bigger than or equal to negative 1. Right? And we could write those in interval notation if we want. But here I'm going to look at, let's say, f minus g evaluated at 2. And we're going to do a few more of these, but let's just start at f minus g evaluated at 2. And I'm going to give you guys a chance to do it first, just so you have a chance. And then when you get an answer, put it in the chat, and I'll know that's enough time for me to then at least go through and solve it for everybody else. So I'm not necessarily expecting you to work this fast, but at least you have a chance to think about what's going on. I don't move too quickly for you. Okay, so what do we get for f minus g at 2? And here you can write your answer in terms of square roots, right? Because you'll sort of have to. Okay, so Jordan's got it in decimal form here. Kate's got it in decimal form. Okay, cool. So definitely affinity will take your decimal form, but it'll also take something like this. So here you have f of 2 minus g of 2. You plug it into the formula. Everywhere you see an x, you replace it with a 2. So this is 1/2 here, 1 over 2. And then this one, everywhere you see an x, you replace it with a 2. So here we'll get g of x is equal to the square root of 2 plus 1 here. And therefore, we get 1/2 minus the square root of 3. And affinity would be fine with this answer, right? You could type it in just like that. Actually, you could type it in like this because it's a graphing calculator, and it would accept your answer up there as well. Okay, so let's now do f times g at 3, just so everybody, we can make sure everybody has the hang of it, and then we'll be done with this and move on to composition. So f times g at 3, it should be f of 3 times g of 3. What do we get? This one's just a nice old fraction for us. Okay, so we've got 2/3 coming in. Let's see how that's correct. So f of 3 is 1/3, 1 over 3. That's this guy. G of 3 is the square root of 3 plus 1. Now the square root of 3 plus 1 is just the square root of 4, right? So this is the square root of 4, and the square root of 4 is 2. So this is 2/3. Okay. So 2/3 for that guy. Let's try f of g, f divided by g at -1. And this is something that might show up in your infinity homework depending on sort of the randomization for your problem. So maybe your classmates may not get something like this, but depending on the random numbers that you get for your answer, you may end up with something like this, right? So let's talk about it. So here we're doing division, and division just means you take the input, plug it into f, take the input, plug it into g, and then divide, right? And there's a problem here. Can somebody tell me what the issue is? What do we get? Yeah, we got the square root of 0 down here. So -1 plus 1. So we're dividing by 0, right? And you can't divide by 0. So this is undefined. Another way to understand that is that -1 is not in the domain of f divided by g, okay? And we could have come up with a formula for f divided by g at x and then figured that out, but here, can't divide by 0. Again, that's because that denominator is 0, okay? So if you run into some problem as you're plugging things in, like you're taking the square root of a negative or something like that, you'll just write that there's no answer here, right? There's no output for that given input. Something goes wrong, and that's because the input isn't in the domain, right? That's what's going on there. Okay, so let's talk about the domain of one of these functions. So one last thing here with these two same functions. What is the domain of the sum? And just as a reminder, the definition is f of x plus g of x, right? So what is that domain here? And we have to think about the domains of these pieces. So let me remind you of this. This domain is everything except for 0. So we would go -infinity to 0, 0 to infinity, and we put parentheses to show that we don't include 0. This domain is everything that is bigger than or equal to -1, and that's because you would set up the equation x plus 1 is greater than or equal to 0, and you would solve it, and you would get the interval from -1 to infinity. Okay, but now you have to combine these together to determine what the domain of the sum is, right? Because both f has to be defined and g has to be defined. So what's the domain of the sum? By the way, the formula for this is just 1 over x plus the square root of x plus 1. So what's the domain? Well, we certainly have to be bigger than or equal to -1, right? Because otherwise it wouldn't make sense to plug it into G. But there's something else that we can't be equal to either, right? Yeah, so we can't be equal to 0. So the way we would write this domain out is we go from -1 to 0, not including 0, and then we'd have to go 0, not including 0, all the way out to infinity. And this is saying it's the numbers bigger than or equal to -1, excluding 0. And this sort of thing does show up in the infinity homework assignment, right? So the reason why is that you have to be able to plug it into this, and you have to be able to plug it into this. So this one has to be bigger than or equal to -1, and this one can't be 0. Okay, so there's your domain for that guy. And if you were looking at f divided by g, You'd also have to be worried about the cases where G was equal to 0. Okay? But I think that's enough for this business, this first one, right? Algebraic operations. And again, I'm spending so much time there because I think it's your best way to understand what a composition really is, right? Okay, so let's talk now about compositions and sort of a different way of putting two functions together. So not only is there addition, subtraction, multiplication, and division of two functions, but there is a fifth operation that you can't normally do to numbers, right? So you can add numbers, you can subtract numbers, multiply and divide, but you can't form the composition of two numbers, right? And the formula that you're seeing here is the definition. So you use a small circle to indicate the composition of two functions. So here's the function f, the function g, and we read this as the composition of f and g. And we want to know, okay, what's the output when we plug in x? Well, what you do is you plug x into g. So x is the input of g. And then you take the output, which is denoted by g of x, and you plug that into the input of f. And that's what this whole expression is down here, f of g of x, right? And the picture is similar to what we had before, but instead of being in parallel, they're what's called in series. So here's our function, say f with its output. I'm sorry, let's put g first here. So here's x going in, and then the output is g of x. And then what you do is you take this g of x and you plug it into the function for f. And what you get out now is not f of x, but instead f of g of x, because you didn't plug in x into the function, you plugged in f of g of x. And this whole sort of bigger function here is what we call the composition of f and g. Okay. And you'll notice in the picture it's a little bit backwards, right? So the g comes first, so that means that you plug into g first, and then the f afterward. That means that you plug into the f afterward. Okay? And that's what this sort of definition that you're given here from the textbook is saying. F composed with g, that's what that little circle is f of g of x. So x is the input of g, and then the output of g, which is denoted by g of x, is now the input to f. And so that's why we put f of g of x, right? And so instead of putting them sort of parallel to each other, we're putting them now in series, right? So we're running the input of one into the, the output of one into the input of the other one. Okay, and like I said, recognizing that something is a composition is incredibly important for those of you going on to calculus, because it'll dictate how you sort of proceed with the question in calculus, right? You'll need to sort of look at a function and see, is it a composition of sort of simpler functions? But in order to get to that level, we need to sort of actually use function composition. So like I said, we're not always just going to be given an expression. Sometimes we'll be given the graph, and we should be able to evaluate things like f of g of 1. So this is a composition of the functions f and g. And what you're seeing here is the graph for f, that's over here, and here is the graph for g. And what we're going to compute here is f composed with g evaluated at 1. So f of g of 1. Now, the first thing that you want to do is plug it into g, right? So this is the inside of this f parentheses here is just g of 1. So what is g of 1? Right? In the chat, once you know what g of 1 is, toss it into the chat box, and we'll go from there. Remember, this is the function g. So what is g of 1? I should put that down here. Okay, so a lot of people are saying 3, and that's correct. The way that you evaluate a function, remember on a graph, is you move along the x-axis to the value you want to input, in this case 1, and then you draw the vertical line going through 1. That's this gray line right here, and it intersects the graph in at most one spot. So that's this point right here, and then you track over to the y-axis, and there the output would be 3. So g of 1 is 3. Okay? So this expression right here is equal to f of 3. Okay? So to finish off this composition, we now need to go over here to f and figure out what f of 3 is. So what is f of 3? Yeah, it's 6, right? So here's 3, boom, we hit the graph there, and we track back over, and we get 6. So here, f of 3 is equal to 6. And overall, the composition, f of g of 1 is equal to 6. Okay? We should now compare this to the following, g of f of 1, because it's different. Okay? So now we want to compute g of f of 1. It's not the same thing. The order of the composition is incredibly important. F composed with g is not the same thing as g composed with f. It's not like addition or multiplication. Okay, so the first thing that we need to do in this one is compute f of 1. Okay, so what is f of 1? F of 1 is 2, right? So here's 1, boom, hits the graph there, and we track back over and we get 2. So f of 1 is 2. And that means I can just replace this whole f of 1 with 2. So g of f of 1 is g at 2, right? So what is g at 2? It's 0, right? It hits the graph right there at the x-axis, and if we track back over to the y-axis, it has a value of 0. So g of 2 is 0 in this case. So the point of this example is that the order of the composition really matters, right? And then also you should be able to do this from the graph itself. So not only just from sort of the equations, but from the actual graph. Okay, so let's do an example where we do things with the equation. Oh, and I guess I should say a quick word about domain before we get too far. So how do we find the domain of a composition? Well, it's much harder than if we're looking at the sum or the subtraction, because we first have to find the domain of G, and we have to find the domain of F. Okay? And that's what we did before, and we just tried to combine those before, but now we have to think about what's going on, right? So we need to find the inputs X such that the domain of G, give me one moment, guys. Okay, sorry about that, guys. So here, what I was saying was we have to sort of look at the inputs X and the domain of G such that when we plug in X, G of X is actually in the domain of F. And if it's not, then we have to exclude that. So it's a pretty tough sort of situation to find the domain, but we'll sort of cross that when we get there with an example, okay? So let's look at a quick example of how to compute the composition directly from equations, and then we'll go from there, okay? So let's let f of x be equal to negative 5x squared plus 1, and g of x be equal to x plus 2. And what we want to do is compute f composed with g at x and get a formula, and compare it to g composed with f at x. Okay? So we want to go ahead and get a formula for both of these guys. Okay, so this one here is going to be f of g of x, and the g of x here is x plus 2. So everywhere we see the g of x, we'll replace that g of x with x plus 2, and we get f of x plus 2. And now what we do is sort of what we did back in the section where we were talking about functions. If we want to evaluate f at x plus 2, all we do is go to this equation, and everywhere we see an x, we replace that x with the input, which is now x plus 2. So this formula here would be negative 5 times x plus 2 squared plus 1. And this is now the new formula for the composition of f and g. Okay? So here we have a new formula for the composition of f and g. And you'll notice that one nice thing about computing the formula like this, it sort of tells us the domain is all real numbers, because you could plug in anything for x here, and you'll get an output. Okay, so let's see what happens when we do it in the opposite order. We're going to get something different, a different formula here. This one's g of f of x. This means g of f of x. So we plug into f of x first. That's the negative 5x squared. So we'll get g of negative 5x squared plus 1. And then we use the formula for g. Everywhere we see an x, we replace it with that input. So we get negative 5x squared plus 1 plus 2. Okay, and we could combine the 1 and the 2 into a 3 there, but that would be the composition of the two of them. Okay, in the last 3 minutes, let's do one final composition and talk about the domain, because that's probably the hardest sort of question that you'll see on the homework assignment this week. So let me go ahead and put those guys up. This one wasn't too bad because the domains here were just all real numbers, right? So there was no sort of real issue with sort of messing up an input with an output. But if you have more subtle functions, then that's a possibility. So this is the last example we'll do, number 6. Let's let f of x be equal to 1 over x minus 2, and g of x be equal to the square root of x plus 3. And you'll notice now that the domain of this function is all numbers except for 2. So we can plug in everything except for 2 here. And this one is all real numbers, I'm sorry, this one over here is all real numbers that's a plus. So this is all real numbers bigger than or equal to negative 3. Okay? And here we'll do the same computation. So let's compute or find a formula for f composed with g at x and g composed with f at x. And then we'll talk a bit about the domain of f composed with g. Okay? So here, f composed with g just means plug the g of x into the input of f of x, right? And you write it in the same order, right? So f of g of x. G of x was that square root of x plus 3. So this is f of the square root of x plus 3. And then here, now everywhere you see an x in this formula, you replace it with the input. So this is just going to be 1 over the square root of x plus 3. And then you subtract 2 from that. Okay? And like I said, let's think about the domain here really quickly. First off, you have to make sure to plug in something that's bigger than or equal to negative 3. So x has to be bigger than or equal to negative 3 for the domain, for this piece. But then we also have to make sure that x is not equal to 1, right? Because if I were to plug in 1 here, I would get 1 plus 3, which is 4. The square root of 4 would be 2, and 2 minus 2 would be 0. So this would lead to a value that was dividing by 0. So combining the two of them together, we've got to go from negative 3 all the way up to 1. We want to exclude 1, and then all the way out to infinity. And that would be the domain of this composition of f and g. Okay, so class is officially over. I'm going to do one last thing here, the composition of g and f. So if you've got to head out, thank you for being here today. You can head on out. But this one last question, I'm just going to do it in the opposite order here. G composed with F, and then we'll be done. Okay, so just going the opposite direction here. G composed with F. Evaluator at X. And in this case, that's G of F of X. You have to really be careful about the order of the composition. It's going to give you something completely different. So now, here my F of X is now 1 over X minus 2. And my G of X is this formula. So everywhere I see an X, I'm going to replace it with the 1 over X minus 2. So this is going to be the square root of 1 over X minus 2 plus 3. And this one is pretty tough because if you want to find the domain, you've got to figure out when this thing over here is positive. We haven't talked about anything quite that difficult yet, but if you guys have questions from Infinity, just let me know, and I'll help you out with them. Okay, have a nice day, guys. Thanks for being here.